All right, thank you for the kind introduction, and also thanks a lot to the organizers for inviting us and giving me the opportunity to show you my recent work, where we actually used the s-SNOM system to look at phase transition materials. In this case, I want to show you a very prominent material in the case of active plasmonics, but also in hydrogen storage materials, which is simply magnesium, as this material, the metallic magnesium, changes to magnesium hydride, which is a dielectric, when you expose it to hydrogen. It has been recently been used. Is it not working? Then I do it like that. It has been recently been used to realize active plasmonic systems where you can change the optical properties of plasmonic systems drastically when exposing such magnesium disks to hydrogen, and therefore create a dielectric magnesium hydride disk. Also to do some polarization control with switchable meta surfaces, but also magnesium, this phase transition from magnesium to magnesium hydride might hold great promises in future prospects, in future applications for new color displays. What becomes very important for all such kind of applications, especially when we go to these really small nanoscale applications, are the hydrogen diffusion properties. And they have been studied many times in the past years, past 10 years, where people mostly looked at a so-called far-field hydrogenography on mostly magnesium thin films, where you see in the pristine magnesium film, hydrogen enters the system and the transmission of the material becomes higher, which are indicated here by these nucleation, wide nucleation centers of magnesium hydride. However, when you look at such a process on the macroscopic scale, as it is done here, for example, here on 2 millimeters, you actually see that this hydrogenation process is very slow. So when we look at such a macroscopic diffusion front, as it is similar to here, when the diffusion front progresses from this area to this area, this takes several minutes, several hours. As you see it here, it takes up to 60 minutes to go, 180 minutes to start actually, and then after that 6 hours to trigger the whole nucleation and growth process. So what we were interested in is to see what is the limiting factor of this rather slow macroscopic hydrogen diffusion in such a system. And this is exactly where our s-SNOM comes into play. We use this to do now not far-field hydrogenography, but do near-field hydrogenography. We have done this recently, however, at a first project to look at the hydrogen absorption and desorption process in individual magnesium nanodiscs. And what I want to show you now today is that we can go even further. So we can really analyze dynamic processes with the s-SNOM system and watch really the hydrogen diffusion and see what is the influence of the nanoscale morphology and so on and so on. How are we doing such an in-situ SNOM measurement? We are simply using a gold grid which has a 2 to 3 nanometer palladium layer already coating on top. Then we take another layers of palladium, titanium, and finally a magnesium layer, and then we put everything on top of a hydrogen in-situ gas flow cell, where the hydrogen now can enter the system through the gold grid or in between the gold grid into the freestanding films and switch really the top surface of magnesium to magnesium hydride, while we are using our AFM tip or SNOM tip in this case to really raster scan the surface. So as we have heard many times, this simply gives us at first a AFM image, meaning we get the height information as well as the AFM phase information, meaning the mechanical phase information. When we now take our laser, which is provided in this case by Stuttgart Instruments, and we shine it into the tip region or in the interacting tip region between the tip and the sample, what we get is we get information of the scattering amplitude as well as the scattering phase. How does such a magnesium film now look like when we trigger this phase transition from magnesium to magnesium hydride? We are imaging here at a consistent or a really narrow band illumination frequency around 1280 wave numbers. And you see when we now add some certain hydrogen amount into our system, you see that the height changes slightly. So we get really a volume increase because we switch to magnesium hydride in this case. We get a certain change in the mechanical phase, because you clearly can see here the grain boundaries, and obviously when you have a volume expansion, also the grain boundaries, grain boundary density, and so on changes. When you look at the scattering amplitude, you see actually that this is highly influenced by the topography itself, by the nanoscale morphology, and simultaneously also, obviously because we change from metal to dielectric, is also influenced by the optical properties, which at the first sight does not give us that valuable information because it is actually influenced by these two quantities. However, when we look at the scattering phase, and this is exactly where the magnesium hydride phonon comes into play, we are really imaging at 1280 wave numbers where we have a characteristic phonon of magnesium hydride causing a really high absorption in the material, which mostly shows a high scattering phase difference between blue magnesium and red magnesium hydride. Let me quickly come back to the mechanical phase. You see here perfectly, as we want to track also the nanoscale morphology and really show later and watch where in the magnesium film on the nanoscale is the hydrogen entering the system. What we are doing, we are simply extracting here from the mechanical phase with a Gaussian filter the grain boundaries of the magnesium film and of the magnesium hydride film. We plot them on top of the scattering phase, which now allows us to really tell where the magnesium is switching to magnesium hydride. Quickly, as we are here on the s-SNOM conference, I also wanted to show how we are actually using here the nano-FTIR setup to really do spectroscopy on magnesium and really on magnesium hydride and really resolve this broad infrared active phonon of magnesium hydride. You see here for magnesium you have a spectrally flat appearance, but when you switch to the magnesium hydride phase and you take a nano-FTIR spectrum on the red areas I showed you on the previous slide, you perfectly see here you have a high near-field absorption, you have a really high contrast enhancement between magnesium and magnesium hydride. So what does such a video now, what I call it, where we are watching really the hydrogenation process, we add several minutes of hydrogen into our system, and you can perfectly see how the evolution happens, how the hydrogen enters the system. For example, when I stop this video here at around 2.5 minutes, what you are seeing is that the hydrogen actually happens, or the diffusion process happens at grain boundaries first. Everywhere we have these black lines, there actually the phase change is appearing, and we have certain areas exactly at these grain boundaries where the hydrogenation process starts first. From there on, the hydrogenation process happens similar as on a far-field scale or in a nucleation and growth process. So what you are seeing, for example, I want to draw your attention to this little crystallite here on the side of the magnesium film. You see here is a certain grain boundary, and here the hydrogen enters the system, and from there it is diffusing laterally and switching all the adjoining nanocrystallites to magnesium hydride. Until then, the hydrogenation process stops for a certain period of time when it has reached this big grain boundary here covering the nanocrystallite of magnesium. So when we go on and go on and go on and go on, what you are seeing is that actually after certain like 20 to 30 minutes, these magnesium hydride channels are forming, meaning not the whole film on the surface is switching to magnesium hydride, but it is forming these kind of magnesium hydride channels. And last but not least, especially after 10 or 20 minutes, you are seeing that the diffusion becomes significantly slower, because the reason therefore is actually simply that the more hydrogen you add to your system, the more magnesium hydride you are generating, the slower this diffusion process becomes, because magnesium hydride itself is actually limiting the further hydrogen diffusion and reduces the diffusion speed of hydrogen in your, in this case, magnesium hydride films. So one really, and that's what I mentioned at the beginning, one really important thing what we can learn from here, from this little video of this watching process, which is simply measured with a near-SNOM setup, is that we can now extract dynamic processes. So we can really extract how are the dynamics here happening. And this is not only for the entire film, so what we can do is we can track the relative hydrogenated area of magnesium hydride and normalize it to the whole size of the grain. So we can really track how is the diffusion dynamics, how are the diffusion dynamics of magnesium hydride, of the hydrogenation uptake of individual grains on the nanoscale. And you see that they actually load significantly faster when I go through all these grains and compare this now to the entire film diffusion, you see that the individual grains, they load significantly faster than the entire film does. Of course, just as a cross-check, here we have the entire film, and we normalize the relative area or the hydrogenated area to the total field of view, which is approximately 1 micrometer squared. When we do the same thing and we normalize only to the areas where we have magnesium hydride being formed, meaning we leave all the blue metallic areas out, you still see, especially when we have a little zoom in, that all the individual grains are loading with hydrogen significantly faster than the whole grain. So to get back to my initial image where we looked at the macroscopic diffusion and asked ourselves, is the nanoscale diffusion itself and is the nanoscale morphology influencing or the limiting factor for this rather slow process? The answer is actually no, because as we have seen on the video, on this little video I showed you on the slides before, when we look at such a diffusion front progression in the far field as it is happening from here to here, what you're seeing that actually in the far field is very slow. But when you look on the nanoscale, the individual crystallites, they switch one after each other very, very fast, and after that, the hydrogenation stops for a certain period of time until the progression goes on. So as a little hypothesis, how can we improve the diffusion kinetics? It can, for example, simply be done when we increase the size of the grains, meaning when we have single crystalline grains which are really, really big, then we obviously have a higher energy boundary to trigger the phase transition in this grain, but it will progress through the whole grain very, very fast. And the other possibility would be to have grains where we have a higher grain boundary density, because when you see the initial hydrogenation process happens always at grain boundaries first, and then when you have a higher grain boundary density, what would happen? Obviously, you have more and more grain boundaries there at that grain boundaries switched simultaneously, which would also explain, for example, why alloyed systems show such an improved diffusion kinetics. So with this, I would like to quickly sum up. I've shown you that we are using the s-SNOM to do in-situ near-field investigations of the phase transition from magnesium to magnesium hydride, and really can learn how the hydrogen diffuses into your system, how the nanoscale morphology is influencing such a far-field process. And last but not least, I've shown you that the individual grains are single crystalline, but they are mostly much, much faster than the entire far-field hydrogen diffusion. With this, I would like to thank all the funding agencies, neaspec again, and you for your attention. Thank you.